Hello, dear students. Today we will focus on our goals for reaction energy, which include identifying energy changes, explaining the differences between exothermic and endothermic reactions, and analyzing real-world applications. At the end of the video, you will be able to identify whether energy is released or absorbed during a chemical reaction, explain the difference between exothermic and endothermic reactions, and analyze real-life examples of chemical reactions and determine the energy changes involved. To guide our study of chemical energy, we will focus on our third essential question. We want to know how we can tell if a chemical reaction releases or absorbs energy. This question connects our laboratory observations to the thermodynamics of molecules. It is like trying to determine if a campfire is heating its surroundings or absorbing cold air. So the key point here is that we are looking for the thermal signatures of chemical changes. Every chemical reaction involves energy because bonds between atoms are either broken or formed. When bonds are broken, energy must be absorbed, and when new bonds form, energy is released. This difference determines whether a reaction gives off energy or takes it in. The energy change can appear in different forms, such as heat from a warm reaction, light from a flame, electricity in a battery, or sound in explosive reactions. According to the law of conservation of energy, energy is not created or destroyed. It is simply converted from one form to another. So when we say we use energy, we are really just changing its form. Enthalpy is a way of tracking heat energy in chemical reactions. It represents the total heat content of a system under constant pressure. During a reaction, we are usually interested in the change in enthalpy, written as delta H. This value compares the energy of the reactants with the energy of the products. If the products have less energy than the reactants, energy has been released. If the products have more energy, energy has been absorbed. Delta H tells us both the direction and amount of heat flow during a reaction. Understanding this concept helps us predict whether a reaction will warm or cool its surroundings. These diagrams help visualize how enthalpy changes during different types of reactions. In an exothermic reaction, the reactants start at a higher enthalpy than the products, and the difference is released as heat. This is why delta H is written on the product side of the equation. In an endothermic reaction, the products have higher enthalpy than the reactants, meaning energy must be absorbed from the surroundings, and delta H appears on the reactant side. The vertical distance between reactants and products on the diagram represents the enthalpy change. Enthalpy describes the heat energy of a system, and changes in enthalpy show how heat moves during a reaction. In an endothermic reaction, heat flows from the surroundings into the system, causing the surroundings to cool down. In contrast, an exothermic reaction releases heat to the surroundings, often dramatically. Let us examine how enthalpy changes appear in actual laboratory experiments. On the left side, we see a reaction where heat flows from the surroundings into the chemical system. Because heat is being absorbed, the temperature of the water drops significantly. This is a clear example of an endothermic reaction. On the right side, we see a dramatic reaction that releases a large amount of heat energy. This heat flows into the surroundings, causing the temperature to rise rapidly. Think of this like sitting near a cold block of ice versus standing next to a warm radiator. So the key point here is that the thermometer tells us where the heat is going. Now that we have mastered energy changes, let us explore how society harnesses these chemical and physical forces. Energy is a fundamental part of modern life, supporting activities such as lighting, transportation, and communication. We harness energy from a variety of sources, including fossil fuels, biomass, geothermal energy, hydropower, batteries, and solar cells. Each source uses a different method to convert energy into a usable form. By learning how these energy sources work, we gain a better understanding of everyday technologies and their impact on the environment. This knowledge is especially important as societies move toward more sustainable and renewable energy options. Let us look at our first two sources, which are fossil fuels and biomass. Fossil fuels such as coal, oil, and natural gas are commonly used energy sources. When burned, they release heat energy. This heat is used to boil water and create steam. The steam spins turbines that are connected to generators, producing electricity. This basic process is used in many power plants and even in engines that power vehicles. Fossil fuels have played a major role in industrial and technological development. Fossil fuels are energy-rich materials formed from the remains of plants and animals that lived millions of years ago. Coal, oil, and natural gas are found in sedimentary rocks and contain stored chemical energy. In a coal-fired power plant, coal is burned to produce heat. This heat converts water into steam, which then drives turbines connected to generators, producing electricity. The process also releases waste materials and emissions that must be monitored and managed. Biomass is an energy source made from organic waste such as food scraps, plant material, and animal manure. When this material decomposes without oxygen, it produces methane gas. This gas can be burned to generate heat or electricity. Biomass systems are often used on smaller scales, such as in rural areas or local power generators. Because biomass comes from recently living materials, it is considered a renewable energy source. Let us now explore our third and fourth energy sources, which harvest the heat and mechanical forces of our planet. Geothermal energy comes from heat deep inside the Earth. In geothermal power plants, this natural heat warms underground water, producing steam or hot water. The steam is brought to the surface and used to spin turbines connected to generators, producing electricity. Afterward, the cooled water is often returned underground to continue the cycle. Geothermal energy is most effective in volcanic or geologically active regions. Hydropower energy is generated using the motion of flowing water. Water stored in reservoirs flows through large pipes called penstocks, which direct the water toward turbines. As the turbines spin, they turn generators to produce electricity. Hydropower plants are often built near rivers or dams, where large volumes of water can be controlled. This process produces electricity without burning fuel. Finally, let us look at the last two energy sources which drive our personal electronics and clean transportation networks. Batteries store energy in the form of chemical energy. When a battery is in use, electrochemical reactions occur inside it, causing electrons to flow through an external circuit. This flow of electrons produces electrical energy that powers devices. Batteries are commonly used in everyday technology such as mobile phones, laptops, and electric vehicles. Unlike power plants, batteries deliver electricity directly without producing steam or mechanical motion. Solar cells, also called photovoltaic cells, convert sunlight directly into electricity using semiconductor materials. When light strikes the solar panel, electrons are set into motion, creating an electric current. Unlike fossil fuels, these energy sources do not rely on burning materials to produce heat. Together, batteries and solar cells play a key role in renewable energy systems and sustainable technology. Let us review the major concepts from this lesson. Chemical reactions always involve energy, because bonds must be broken and new bonds must form. Bond breaking requires energy, while bond formation releases energy. To measure heat changes under constant pressure, chemists use enthalpy, represented by H. The change in enthalpy, delta H, shows the energy difference between reactants and products, and tells us whether a reaction is exothermic or endothermic. Beyond the laboratory, energy powers our everyday lives and comes from both natural and man-made sources. Understanding these principles helps us make informed and more sustainable energy choices. Think about this. How are chemical reactions connected to technologies you use every day? To answer the essential question, we can determine this by observing changes in temperature, light emission, or gas production during the reaction. If the surroundings become warmer and energy is released, the reaction is exothermic. If the surroundings become cooler and energy is absorbed, the reaction is endothermic. For your exit ticket, name one example of an exothermic reaction, describe one energy source and how it is harnessed, and explain how energy changes affect reaction usefulness.